right, so last time we did the disk method, which you're taking an area and revolving it around an axis. This is the same thing. This is called the washer method. The only difference between disks and washers is the washers have a hole in them. So all of the shape, all those three-dimensional objects that we did last time were like solid the whole way through. These ones are going to have a hole in the middle. I wish that they would give up calling it the washer method and just go ahead and call it the donut method. That's what everyone calls it anyway. But do you guys know what washers are? Like if you go to the hardware store, do you know they have like screws and bolts and stuff? Do you know like what washers are? Like they're these things. They're like little metal. Okay, you guys know what I'm talking about. It's like a little metal disc that, well, not disc. I shouldn't say disc because disc is the other thing. Anyway, it's like that and it's got a hole in it. Yeah, like a flat metal donut. Perfect, Ethan. Thank you. Like coins, but with, see, you guys are creative, like a coin, but with a hole in it. Oh, did you know that some currencies, like in other countries, their coins do have like a hole in it? That's cool. I think that's interesting. Anyway, that's what a washer is. This is the exact same thing we did last class, except they're all going to have a hole in it. Yeah, I don't know. I don't know what country it is. You could Google that, I suppose. I don't know. I can't remember. I know some country does it because I've seen them, but I can't remember. I should have known what I was talking about before I started to say that. Anyway, I know it exists. That's what a washer is. These are all going to have a hole in it. It's the exact same thing. So when you set these up, you're going to have an outside radius and an inside radius. So the outside radius would be like the whole way to the outer edge. And then the inside radius is just that part. So you're subtracting out the negative space in between. So it's instead of just pi r squared, it's pi r squared minus r squared. It's like you've factored the pi out. Still, if you go around a horizontal axis like the x-axis, it's going to be dx. Vertical like the y-axis is going to be dy. All right, and that's the exact same thing. We're just going to do a bunch of practice. Off we go. All right, so number one, find the volume of the solid generated by revolving the region bounded by the parabolas. All right, y equals x squared. So we'll have 0, 0, 1, 1, and 2, 4. So here is that parabola. And then y squared equals 8x. We're going to have to get y by itself because we're revolving around the x-axis. So it's going to be a dx problem. So we're going to get y by itself. We're going to square root both sides. Be y equals square root of 8x. So still plugging in some numbers. If you plug in 0, you're going to get 0. So we're going to start at the origin. Plugging in 1, that's going to give you square root of 8, which doesn't really help without a calculator. If you plug in 2 times 8 will be 16. Square root of 16 will be 4. So that's this point right here. And then you'd have the same thing. You'd have 2, negative 4. It's going to be a sideways parabola. So it would look something like this. And I'm going to end up erasing a lot of these. Make sure you're using pencil. It helps if you can erase. So this is the area we have. It looks like a little leaf, like a flower petal or something. I'm going to erase everything that's outside of that. All right, and we're going to rotate that little like flower petal leaf thing around the x-axis. So here's our ghost shape down here. All right, and so I'm not a fantastic artist. I'm going to make an attempt to draw this for you. Remember, this is spinning. It's going to be circular. So the outside radius is going to go all the way to these outer edges. And then the inside radius is just going to touch the inside edges like that. So what you end up with, I'll turn it this way. You end up with a bowl. And then the inside of it is kind of like this. You know what, let me make it so you can see me again. I can like mime this. Maybe I'm going to try. I'm making an effort here because I don't want to just teach it to you. I want you to understand what we made. So you have a bowl that's like this, but then the inside of the bowl is curved in like that, but it's circular the whole way around. Is this making sense? Are you envisioning this a little bit? All right, so anyway, that's what that's gonna, okay, cool. We're making an attempt. So anyway, do you see how it's like a washer in there? So you end up with donuts. Everyone ends up calling it the donut method. So it's going to be a dx problem because we're going around the x-axis. So this is going to be pi r squared minus r squared dx. Set that up. It makes your life so much easier if you have this like skeleton of the problem, and then you can just go and fill it in. All right, and then you don't forget the pi and you don't forget the squared, and all your parentheses end up in the right place, so just set that up. All right, so we're going to look at our x-axis for our boundaries. It's going to be from 0 to 2. And then I will color code these. So the outside radius goes all the way to this upper graph. So the outside radius, and again, it's upper graph minus lower graph. The lower graph is the x-axis though, so that's 0. Like zoom way in on this. All right, so the outside radius goes all the way to this graph. That was that square root of 8x. So square root of 8x is the outside radius. That goes right there. And then the inside radius only goes to here. So that is this graph. And that was the x squared. So x squared is going to go right there. All right, so this was our outside radius minus our inside radius. So you're subtracting out the negative space in between. All right, so let's simplify this down. Pi integral 0 to 2. Here, the squared and the square root are going to cancel. So that's just 8x minus x squared squared will be x to the 4th dx. And then we will do antiderivative upper boundary minus lower boundary. So this antiderivative will be 4x squared minus 1/5 x to the 5th, such that 0 to 2. And I'm just going to plug in 2. Again, you would do upper boundary minus lower boundary, but if you plug in 0 for these x's, the whole thing's just going to be 0. So plugging in 2 squared is 4, times 4 is 16. And then 2 to the 5th is 32. So that would be 32 fifths. I'm going to go ahead and stop there. That's simplified enough for me. All right, cool. So let's try another one. Find the volume of the solid generated by revolving the semicircular. It's nice when they tell you what kind of shape you're going to end up with. You're going to end up with a semicircle bounded by this. Ooh, big red flag there. It's x equals. This is probably going to be a dy problem. So, let's graph this first, and then we'll get to the rest of this. All right, so plugging in some values. Let me make an XY chart. We're going to plug in y and get x. I'm going to start with 0. If we plug in 0, we're going to get square root of 4, which is 2. All right, so we get 2, 0. So right here, oops, let me zoom out a little bit more. So this point right here. And then I'm not going to do 1 because that would give me 4 minus 1. That would be 3 square root of 3. I don't want to deal with that. So let's do 2. And in fact, it's going to be plus or minus 2. Since you're squaring it, it won't matter whether it's positive or negative. 2 squared would be 4. 4 minus 4 is 0. So we get 0, 2, and 0, negative 2. And here is our semicircle. And it said the other graph is the y-axis. So this is the y-axis. And so here is our shape. All right, now we're going to revolve that, spin it around the line x equals -1. So I'm going to dot that in. This is our axis of rotation, x equals -1. So it's like we just took the y-axis and scooted it over a little bit. So it is going to be a dy problem. We're not going around the y-axis, but it's still a vertical line like the y-axis. So I'm going to draw my ghost shape over here, and then we're going to try to envision what this looks like. Remember, it's round. These are all round. They're all circular because you're spinning them. You have to imagine this thing spinning. Your outside circle is going to go all the way to the edges. And then the inside circle is going to be this part. So can you guys imagine what this looks like? Like it's an orange that somebody like punched a hole through or something. Or can anyone come up with something else that it like resembles? Or are you like imagining this? Like, what could this be? Be creative. Anyone have an idea? Like imagine this three-dimensional object, and then like this part in the middle is missing. A very round plastic Easter egg. Yeah, and like someone like poked a hole through it. Or an apple without its core. Cool. Or like if you imagined it being very, very tiny, it's like a bead that you could string onto a necklace, or a cut coconut. Okay, good. You guys are awesome. Okay, cool. That's what I want. I just want you to imagine it because it is three-dimensional. All right, so we're going to have pi r squared minus r squared dy. Again, set that up. You won't miss anything if you go ahead and set that up. And I'm going to ask you guys the boundaries. It's dy, so look at your y-axis. This is going to be from where to where. So look at your y-axis when you decide your boundaries. What are our boundaries going to be, guys? Good, you guys rock. -2 to 2. And a lot of time on the AP exam, well, a lot of time, this is usually how they do this. Usually when they have you set these up, it's worth 3 points. And you get a point if you put the pi and you have the boundaries correct. So this by itself is worth a whole point, which is fantastic. All right, so let's color code. This is our outer radius. It's going to go from the axis of rotation all the way out to the edge. So it is right graph minus left graph. Right graph minus left graph. So the right graph is this semicircle. That's this square root here. So square root 4 minus y squared minus the left graph is this x equals -1. So it's right graph minus left graph. Now, yes, those will cancel and it'll be a positive one. I'm just trying to show you it's right graph minus left graph. And then the same thing is going to happen here. Let me color code for the inside radius. The inside radius is this portion. And again, it's right graph minus left graph. The right graph in this case is the y-axis, that's 0, minus the left graph, again, that's the axis of rotation, that's the -1. Now, again, those would cancel and it would be a +1. And what I have most people do is they'll go, hey, Miss Cole, the distance from here to here is 1 unit. Like, so I know that this inside radius is just 1. So you can do that as well. You can just go, oh, well, from here to here is just 1. But it is right graph minus left graph is where that comes from. Now we are just going to stick this one in the calculator, but I am going to like simplify this down and make it look a little bit nicer here. These negatives will cancel. That'll be a +1. And then this is just 1. But I would not make you work this one out by hand. So let's go ahead and type it in. All right, so pi integral -2 to 2, parenthesis, square root 4 minus x squared, again, type x because you have an x key, +1, close parenthesis, squared, minus, now it's 1 squared. You don't even really have to put that squared because 1 squared is just 1. I'm just typing it to be thorough. And then dx, and it will give us our answer eventually. Any data. There we go. 72.988. Yeah, on the test, I'm going to have you do most of them I made most of them easy enough that you could just do them by hand. I think there's 2 that got a little wacky that you can use a calculator for, and I put it on directions on the test. I just typed it on there. These are the ones you can use a calculator. So yes, you know. And in the homework, you know as well, because if your answer choices are all decimals with 3 decimal places, then obviously you need a calculator. Now, what I did for all of these, just to make things a little bit simpler for us, we're going to use the same shape for all of these. We're just going to revolve around different axes of rotation. All right, so consider the first quadrant region bounded by y squared equals x. That's your regular old parabola, but just turned on its side. So we're going to have 0, 0, 1, 1, 4, 2, and -2. It's going to be the sideways parabola, since x and y are reversed there. Again, it's not a function, but we don't mind. All right, the x-axis and the vertical line x equals 4. So this is the shape that we're going to use for all of the problems on this side of the paper. So I'm gonna go ahead and erase these tails off of here. And what I'm gonna do is I'm just gonna go ahead and take a minute. Whenever I teach this, I just tell everybody, go ahead and just draw that for all the other problems, because that's the same shape we're gonna use for each one of these. So we're using the same shape to start out. We're just gonna revolve it around different axes. All right, so there we go. I just drew that 4 times. And then we'll go back and answer the questions. So for letter A, we're going to revolve around the x-axis. So I'm going to draw my ghost shape down here. And it's going to look like that. So what do you notice about this one? What does it not have? Yeah, good. There's not an inside circle. There's not a hole in it. This is just disk. Yeah, good. There's no hole punched through it. Awesome. So this is just like what we did last time. It's going to be a dx problem. So I need to get y by itself here. Y is square root of x. And so it's going to be pi r squared dx. I threw that on there just to remind you, they don't always have a hole in them. They can, but they don't always. All right, so this one's just pi r squared. There's just one. So our boundaries look at the x-axis. Since it's a dx problem, it'll be 0 to 4. And our radius is upper graph minus lower graph. It would just be square root of x. And so the squared and the square root cancel. All you have is x. That antiderivative is 1/2 x squared. And when you plug in 4 squared is 16, half of that is 8, so 8 pi. So again, I just threw that on there just to remind you, they don't always have a hole in them, so just be aware of that. All right, so letter B, now we're gonna spin this around the y-axis, so it's gonna be a dy problem. And I'm gonna draw my ghost shape over here. So the outside circle is going to go all the way to the edges. And then the inside circle is just going to touch the insides. Like, oh, I actually drew that one pretty good. So again, remember, it's round. You have, outside edges that are all the same. Here again, let me just try to mime this with my hands here. So you have a circular thing it's like this on the outside edges. I don't know which way to go here. So it's like flat around the edges, kind of like a above ground swimming pool. Do you know what I'm talking about? Like an above ground swimming pool. It's flat on the edges, but then the inside is like this. It's a really weird swimming pool. It's like a swimming pool. When you get in, the ground's not flat. It just like does that. Are we envisioning this? I don't know. Making it sense. So, but it's like flat around the edges. All right, so this is going to be, so there is a hole in the middle. So it's going to be pi r squared minus r squared dy. It's dy because we're spinning around the y-axis. So we're going to use y values for our boundaries. It'll be from 0 to 2. And then our outside radius goes all the way to the edge. So it is right graph minus left graph. That would be 4 minus 0, which is just 4. The other thing people do is they'll go, oh, the distance from here to here is 4 units. So that's just 4. But if you still want to think of it as right graph minus left graph, it's 4 minus 0. And then this is the inside radius from here to here. Again, right graph minus left graph. The left graph is the axis, that's 0. The right graph is y squared. So y squared is going to go right there. All right, so simplifying this down before we do the antiderivative here, 4 squared will be 16. Y squared squared will be y to the 4th. And then antiderivative is 16y minus 1/5 y to the 5th. And we just need to plug in 2. So 16 times 2 will be 32. And then minus 32 fifths. Or it's a very, oh, sorry, I just thought it's a very symmetrical skate park. Yeah, I like that too. Or, but like when you went down into the middle, it would come to a point. So you would be like out of luck when you skated down. That's cool. I like that though. But I guess you could go around the edges. Oh, you know what this reminds me of? You know what this actually reminds me of is, do you know those things where you can put a coin in and you watch the coin circle around and around until it like goes down the hole in the middle? Do you guys know what I'm talking about? They do it for like donations places. You put a coin in, and like when you were a little kid, you couldn't walk past one without going, "Mommy, I need a quarter to put in the thing." And like the coin would spin around and around and then it would go down. Okay, that's what that is. That's what that reminds me of. Okay, cool. All right, see, now we're going to spin around the line x equals 6. So let me dot that in. So I'm going to kind of go off the paper a little bit, my ghost shape. All right, so there's x equals 6. And the ghost shape is going to be over here. And I'm sorry, that does kind of go off the paper a little bit. This one's going to be dy. It's like we took the y-axis and just scooted it over a little bit. So it's going to be a dy problem. Outside radius goes all the way to the edges. Inside radius just touches the insides. I'm going to zoom out so you guys can see the picture and what I'm writing at the same time. I know that makes it smaller, but I want you to be able to see it all at the same time. All right, so this is going to be pi r squared minus r squared dy. Again, it's like we moved the y-axis over a little bit. So looking at our y-axis for our boundaries, it'll be 0 to 2. And then let's figure out what the radius for each of these is. All right, so outside radius. It's going to be right graph minus left graph. So the right graph is 6, that's the axis of rotation, minus the left graph, which is this curve that was y squared. So 6 minus y squared. Again, right graph minus left graph. And then the inside radius is from here to here. So you can do right graph minus left graph. It would be 6 minus 4, or you can just go, oh, that distance from there to there is 2. But if you do right graph minus left graph, it comes out the same way. It would be 6 minus 4, which would be 2. So anyway, that's just 2. All right, so now we have to work this out. So 6 minus y squared squared. If you want to write that off to the side twice to help you, you can't be scared of the algebra. We're going to have to distribute all of this to each other. So 6 times 6 is 36. This will be minus 6y squared minus 6y squared. So that's minus 12y squared. And then negative y squared times negative y squared would be positive y to the 4th. And then it's minus 2 squared. So it's minus 4. I'm going to go ahead and combine that with the 36. 36 minus 4 will give us 32. All right, and then antiderivative will be 32y minus 4y cubed plus 1/5 y to the 5th. Oh, sorry, it's such that 0 to 2. And I'm just going to go ahead and plug in 2, because again, if you plug in 0, they'll all just be 0. So this will be pi times 32 doubled, that'll be 64. 2 cubed is 8 times 4 is 32, and then plus 32 fifths. 2 to the 5th is 32. All right, one more. We're going to take the shape and spin it around the line y equals 2. So here is our axis of rotation, y equals 2. I'm going to draw my ghost shape on the other side. And so the outside radius goes all the way to the edges. Then this is the inside radius. So let's think about what that three-dimensional shape would look like. Again, it's round. This would be like a drinking cup, like the outside is round, like a drinking cup, you could, or like a soda can, like you could hold on to, except the inside goes down like that. So it's like a really weird shaped inside of the cup. Like you could pour liquid into it, but like the outside is like a cylinder, but and even Steve skate park, you're a daredevil. Yeah, or another one of those things where if you put a coin in, it's gonna like go down all the way to the bottom. All right, anyway, that's what that looks like. So it's like we just took the x-axis and scooted it up a little bit. So it's gonna be a dx problem of pi r squared minus r squared dx. Oh, the present thing from Polar Express. Yeah, I like that. Yeah, that's exactly what that is, except instead of a coin, it's like a present that goes the whole way down. I like that. Oh, that's such a good movie too. My son loves that movie. We watch that every year. Good idea bringing that up. I like that. Now it's making me think about Christmas. Looking forward to next Christmas. All right, dx problem. So we're going to look at our x-axis. It's going to be 0 to 4. And then our outside radius, again, it's upper graph minus lower graph. Okay, we're bringing back deep memories here. That's good. Upper graph is 2. The lower graph is 0. So that would be 2 minus 0, which is just 2. But the other thing people tend to do is they'll just go, oh, that's a distance of 2 units. Like from there to there is 2 units. And then the inside radius, you zoom in because that's really small, is from here to here, upper graph minus lower graph. So the upper graph is 2. And the lower graph is this curve, which is square root of x. So again, there were 2 versions of this equation, one for the dy problems, one for the dx. Let me come back. This is what we used when it was a dy problem. And then this is what we used when it was a dx problem. One is one way and one is the other. dy has to have y's in it, dx has to have x's. So it was square root of x. And then I'm going to let us just type this one in. You could multiply this out, but that's going to get crazy with all the square roots. I'm going to let us just type this one in. All right, so this will be pi integral 0 to 4. And then 2 squared is 4 minus, let's see, 2 minus square root of x, close parenthesis, squared dx. All right, so 41.887.